Welcome to Control System Classes. The topic for today's class is overview about time response analysis. The detailed topics for today's class is time response definitions and the expressions of second order system and how it changes with respect to damping and the signals. What is time response? The response of the system as a function of time is called time response. Here, the notations involved are R of S refers to a controlled reference input, C of S represents controlled output in Laplace domain. If it is given as R of t, C of t, those parameters are with respect to time domain. G represents open loop transfer function or plant or process transfer function. H represents the feedback element. Here, the input R of t or R of S corresponds to the desired R reference input. The output C of t or C of S is corresponding to the actual response. So what is time response? The response of the system as a function of time. Here, the time response can be divided into two portions. This is overall time response of any kind of system. Y-axis is output, x-axis is time. Output is mostly in magnitude and the portion is divided into two halves. One is called transient response and steady state response. What is steady state response? Where the output reaches a fixed value. Here, before reaching the fixed value, the output takes many transients. These are called as oscillations, and the oscillations are decreasing with respect to time. So exponentially decaying amplitude is transient response. Afterwards, we have a constant response. This is the total time response is always the sum of transient response and steady state response. And also, as we are discussing about the overview of the time response analysis, I have taken the expression of C of t, that is the response for various cases of damping. What is meant by damping? Damping is nothing but suppression of oscillation. The term damping corresponds to suppression of oscillations. So the system will always have some oscillations. So how to suppress the oscillations? By using an external controllers or compensators, we can control the damping. Right. So based on the values, usually the damping is represented by the sum zeta. What are the values does this zeta takes? The zeta can take a value between 0 or greater than 1. It starts from 0 and it can take any values, right? So mostly when the zeta value is between 0 to 1, we call the system as underdamped system. When the value of zeta varies between 0 to 1, we call the system as underdamped system. When the value of zeta is 0, we call the system as undamped system. When the value of zeta is equal to 1, when the value of zeta is equal to 1, we call the system as overdamped system. So a critically damped system. When the value of zeta is greater than 1, we will call the system as overdamped system. So zeta is equal to 0, damped system. Zeta is between 0 to 1, it is called underdamped system. Zeta is equal to 1, it is called critically damped system. When zeta is greater than 1, we'll call it as overdamped system. When zeta is greater than 1, we call it as an overdamped system. And also, you can see the response here for various, here the input is assumed as step signal. The input is assumed as unit step signal. When unit step signal is applied to a second order system, we got these responses. So second order system, how second order system will be represented? Second order system is nothing but C of S by R of S. C of S by R of S is equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. 2 zeta omega ns plus omega n square. This is the general second order transfer function in closed loop form. So for the system, R of S is given as 1 by S. So when R of S is given as 1 by S, we got these kind of response equation. So by taking inverse Laplace transform, that is to convert to time domain, we got C of t for all the cases like this with respect to the standard second order equations. Now, you just look at the waveform. So, how the waveform is affected? For all the cases, the input remains the same. The central second order equation remains the same. Only cases we have changed the damping. So, you can see here, this is zeta is equal to 0. For zeta is equal to 0, we have fully the system with oscillations. There is no final value reaching. So it is the system is fully with oscillations. And also you can see the expression C of t is equal to 1 minus cos omega n into. So let us assume omega n into t is equal to 0. When omega n into t is 0, cos 0 is 1. So the initial portion is 1. Now let us assume omega n into t takes a value of 90. So cos 90 is 0. So this is the portion of cos 90. Let us assume omega n into t takes a value of 180. Cos 180 is minus 1. So already we have a minus there. So we'll have the answer as 2. So the maximum magnitude will become 2. But what is my desired input R of t? R of t is 1, but my maximum magnitude is 2. So this is so we cannot use undamped system. Damped system, if it is used, it will have only the transient portions and we don't have final value. And also you can see here, for underdamped system, this is my equation, right? So in this equation, let us substitute t as infinity. When you substitute t as infinity, let us assume it is exponential into sine term. So when you substitute t as infinity, what we will obtain when e power minus infinite term is 0. So C of t is equal to 1. It means when zeta is less than 1, the system will have initial oscillations, but it will settle to 1, right? At final value, it will settle to 1, right? So why, what is the shape before reaching the final value? The shape is exponential into sinusoidal. So it will decrease exponentially, but the oscillations will take a form of sinusoidal. That is the meaning behind it. Is that right? So the undamped system, final value is 1. Initially, it has a transient due to this exponential and sine term. Similarly, for critically damped system, the expression involves only an exponential term and sine term will not be available. So it means it doesn't have an oscillation. When zeta is equal to 1, you can see the waveform. This is the zeta is equal to 1. You don't have any sine oscillations. Only the magnitude is increasing exponentially. And then it reaches a final value. We have 1 minus. That's why we have an exponentially increasing term. For overdamped system, we have the expression and it depends on the value of zeta. So based on the value of zeta, the system oscillations will goes on. And you keep in mind when zeta increases, the system will become more sluggish. So this is the waveform of a second order system with unit step excitation for various cases of damping. So the damping is a factor which will contribute to oscillations in transient portions, and when time t is equal to infinite, we can able to predict our final value. So for all the cases when time t becomes infinite, we can able to get the value as 1. For undamped system, it never settles and it will have full of oscillations, and the maximum magnitude it takes is 2. But the target value is only 1 and the final value is 2. So we will not use undamped system. Most of the practical system will go with underdamped systems. Then we also need to know about the test signals. So in the earlier cases, we discussed R of S as 1 by S and we have defined the C of t. So let us revise about the test signals. So the knowledge of test signal is important in order to predict the response of the system. Is it right? We had predict the response in the previous slide. We had discussed about the response of the system. What are the other test signals available? The test signals available are step, ramp, parabola, impulse and sinusoidal signal. This assign is what is a step signal? A step signal is a one whose magnitude is always constant with the final with an integer. So let us assume the value is a. So it is always constant when time t is greater than or equal to 0. When time t becomes less than 0, the magnitude is always 0. And also in control system, we will use unit step signal. So when unit step signal means the value of a is 1. So r of t is 1 for t greater than or equal to 0 is equal to 0 else. So this is my step signal. So it resembles a sudden shock. Then a ramp signal, it resembles a constant velocity signal. So it is constantly increasing. You look at the waveform. When t is equal to 1, my magnitude is a. When t is equal to 2, 2a. When t is equal to 3, 3a, and so on. So with respect to time, the signal will have a linear increase of output. So we can write the mathematical equation as r of t is equal to a into t for t greater than or equal to 0 is equal to 0 else. What will be the value of unit ramp signal? For unit ramp signal, the value of a is 1. So r of t is equal to a into t. Then the third signal is parabolic signal. So this is the parabolic signal. What is the expression? R of t is equal to a into t square by 2. It resembles a constant acceleration. And for unit parabolic signal, Ra is 1. So R of t is equal to t square by 2. The next signal is an impulse signal. An impulse signal is a short duration signal whose magnitude is large at time t is equal to 0 and then the magnitude becomes 0. If it is a unit impulse signal, the magnitude becomes 1 only at time t is equal to 0. Remaining time the magnitude is 0. So this is called unit impulse signal. The Laplace transform of unit impulse signal is 1. The impulse signal can also be represented by the symbol del of t. So let us look at the formulas in time domain and also in Laplace domain. So if it is a step signal, the equivalent Laplace transform formula is a by s. For ramp signal a into t, it is a by s square in Laplace. Parabolic signal a t square by 2. Laplace formula is a by s cube. For impulse signal del of t and the equivalent value is 1. If it is a unit signal, the a can be substituted with the value as 1. The next is how we can get one signal from other signals. For example, if you have a step signal and you are given with integrator or differentiator and with then op-amp. An op-amp made integrator or differentiator, it is given. So what mathematical operations you will perform to convert it to ramp? So step signal, if you perform an integration, it will be converted to ramp. Similarly, a ramp signal, if you perform integration, it will goes to the parabolic. So they are all higher order signals. So we need to perform integration. If you want to decrease a higher order system to a lower order, you can go with the differentiation. So if a step signal is available, it is a constant signal. So differentiation of a constant is 0. But at time t is equal to 0, when you enlarge, you will get an impulse signal. You can also verify it with your CRO or DRSO available in laboratory by doing an experiment with op-amp. Ramp signal, when you perform a differentiation, it will become a step signal. So by that way, we can able to convert one form of signal to other form. And it's all about the class. The next topic we'll discuss about it is poles and poles, zeros, type and order of the